video is about chains of variables. Okay, so it's one of the most useful techniques in order to deal with primitives, right? So suppose we have a function f, right, and we have our primitive, which is right, and suppose we can change we change our variable x to a function of another variable t, right? So if we compute now the derivative of our function f expressed as a function of t, right, applying the chain rule, this is just the derivative of f capital F, which is f small f, but that's what the definition of the primitive is, at g times g prime, right? So in other words, this is going to be like this, right? F at g, right, is going to be the primitive of this expression times g prime at t dt. But g of t is actually x, right? And so f of x is going to be exactly the same primitive, right? So this primitive is going to be the same. Okay, so whenever you have an expression like this, you can always turn into this, finding an adequate change of variable, or the other way around. Okay, the usual way in which we you know, apply this in applications is, for instance, if you say x is g prime of t, sorry, g of t, right? So typically we say, well, dx is d of g prime t dt, right? So depending on the example, you just need to substitute dx times this. Okay, so for instance, let me get you, and okay, maybe this works. So we have, for instance, this primitive, right? Well, this we haven't seen how to compute it, right? But this is obviously e to the x squared, right? So is there any way we can call this t is e to the x, right? And so obviously we have t squared is e to the 2x, right? So now in order to change the t dx, we need to differentiate this, and what we do is we say dt is e to the x dx, right? So e to the x dx becomes dt, okay? And this is t squared 1 plus t squared, if this works at some point. Okay, so what you get is the primitive of 1 divided by 1 plus t squared, which is the arctangent of t. Okay. Okay. Sorry, it took some time to write. And then plus c, of course, plus the constant. Okay. Now you undo the change of variables, you get the arctangent of e to the x plus c. Okay, as easy as that. Now, so typically when you have exponentials, a very you know, immediate change of variables to use t equals the exponential, right? So now we have this dx is the cubic root of 1 minus 2x squared minus the square root of 1 minus 2x. Okay, so in this case it's obvious that we want some expression depending on 1 minus 2x, right? But we also, you can rewrite this as, right, dx divided by 1 minus 2x to the 2/3 minus 1 minus 2x to the 1/2, right? So we want a t such that when you substitute it here, you get rid of the roots, right? So one way to do it is, for instance, to choose the common multiple of 3 and 2, in this case 6. Okay, so if t to the 6th is 1 minus 2x, right, that means that for instance, if you get 1 minus 2x to the 2/3, right? You multiply this by 2/3. This is 12 divided by 3. This is t to the 4th, and then 1 minus 2x to the 1/2 is t cubed, right? So this becomes the whatever this is here divided by t4 minus t cubed, right? We just need to compute what's dt and dx, right? So here is 6t5 equals minus 2 dx, right? And so it's t5 dt, right? So this just becomes and then you have 2 divided by 6 divided by 2, sorry, it's minus 3 t5 dt, right? And now this integral is easy to see because it's just a primitive of rational functions we have just seen, right? So this is, let's say, this is a minus 3, and then we have t5 divided by this, so you can actually divide everything by t cubed, you get t cubed, so t squared divided by, and then you have t minus 1 dt, right? And you can, you know, if you decompose this in partial fractions, what you do get is minus 3, and then you have the primitive of t plus 1 over t minus 1, right? Let me erase some things. Sorry, this is previously decomposed in partial fractions. What you need to do is divide t squared by t minus 1, or do the Taylor expansion of t squared at 1, right? And so this is minus 3, and this is t squared divided by 2 plus t plus the logarithm of t minus 1 plus c. Or in other words, undoing the change of variable t squared, remember that t6 was 1 minus 2x. So this is, let's see, wait a minute, is this correct? Yeah, so this is t squared, so this is 1 minus 2x to the 2/6 or 1/3 if you want, right? And then let's see, you have plus t, which is 1 minus 2x to the 1/6 plus the logarithm of the 6th root of 1 minus 2x minus 1, okay, the absolute value of this, plus c. Okay, so as you can see that, you know, this kind of integral you wouldn't be able to have solved without this change of variable.